Alrighty. Good afternoon, folks. My name is Teho. I guess we can get this session started. I'm part of Samsung research and work in the area as the voice of God spoke in security and privacy. In this talk, we'd like to share with you one part of our journey towards responsibly handling data. This is a close collaboration with Samsung Research and Samsung's Big Data Center. Unfortunately, you might have noticed one of the co-presenters for this talk, Kunhui, could not present. I'll be presenting on his behalf, and we'll have some folks from his team to help in answering any questions you might have after this talk. So we live in a digital world where digitization of personal information is a norm, and it's up to everyone who participates in the digital world to act responsibly. At Samsung, we place a high bar in privacy and strive to work internally and externally to set high standards. At last year's SDC22, we shared with you our privacy principles. Choice, we believe in giving you the ability to choose how your data is collected and used. Protection, security is built into our products and services from the start. Transparency, we disclose how we collect and use your data. We are back this year to share more details on how we are continuously improving our data privacy posture. Today, we'll share with you how we technically approached a particular problem of responsibly handling data. In particular, we'll cover how to detect and classify personal information. We'll share with you what data protection means to us and how we dissected personal information from a technical and operational viewpoint. We'll also share with you how this technology is deployed in our environment. We hope sharing our experience and insights could help developers and operators and others to responsibly handle data within this community. So we'll first proceed with what data protection means to us and give you some background on where we are coming from. We understand all organizations handling data needs to be aware of how to protect it. From our perspective, the important elements in data protection are data discovery, data handling, and data disposal, where data discovery overlays to our principles around choice, data handling overlays to our principles around protection, and data disposal overlays to our principles around transparency. For data discovery, it's all about catalog, classify, and label. For data protection, it's all about encrypt, decrypt, re-identify, compute, and generate. And for transparency, it's all about retain, delete, and destruct that overlays to data disposal. We'll cover primarily the problem of data discovery in this talk. When we take a closer look at data discovery, cataloging defines the format and type and schema of the data. As you can see in the picture that's shown, it's how we organize and format the data. Once we have a catalog, we classify the data for each catalog item. Based on a classification, we ultimately assign a label which drives downstream activities in the data lineage. Next, we'll cover what personal information means to us in the lens of technology and operations. In a technical view, we sort personal information as data that has three attributes: distinctibility, traceability, and linkability. Distinctibility represents the uniqueness personal information may possess, driving us to think about technical ways to better detect and control the degree of distinction. Traceability accounts for the ultimate reference that is inferred by analyzing a sequence of data. This property drives our ability to infer or defer a group or a specific individual. Linkability helps us define relationships between data elements that may result in re-identification when data elements are linked. When we cross-checked these three attributes or properties with our data lineage, we found overall it made quite a bit of sense to us. In an operational view, personal information in the context of data discovery validates purpose, process, and governance. The purpose of the data drives how classification is captured in the forms of labels. Processing of data helps us handle using these classification levels. And ultimately, governance of data helps understand the workflow for retaining, disposing of data through classification levels. Both of our viewpoints, technically and operationally, helped us come up with constructs and expected workflows within our technical approach. Now that we've provided some detail on what we mean by data protection, what we mean by personal information, we'd like to dive into the technical approach itself. We'll be going through some key components and concepts first. So logically, what this meant to us is we looked at two key components that made sense. One was the operator that captured an operational flow, or operators. And another component, the agent, that is the technical logic, or the brains behind preparing, classifying, and post-validating data. In a nutshell, an agent receives data streams from various data providers within our enterprise and is orchestrated by the operator to classify data streams. We ran into some interesting issues which we'll later start covering as our data organically grew and shrank within the enterprise environment. As we describe more details about our architecture, we'll cover how we tackled scalability, certainty, and variability. We chose to develop this technology in-house to ensure we can have a continuity of security and privacy from device to cloud, as well as a means to adapt to the organic growth of our enterprise environment. So if we double-click into the operator from the name itself encapsulated our operational view for purpose, process, and governance. The operator abstracts out how we schedule, dispatch, and orchestrate agents. While we debated on various instances of what we wanted to encapsulate and how we'd like operational constructs to evolve, we found this level of abstraction help us keep pace with the operational model within an enterprise environment. Encapsulating the notion of an operator helps some of the folks charted to be more research-centric or focused around that to look into the evolving agent. The agent contains more research-worthy problems to tackle. If we double-click on the agent, our agent can be further divided into logic that assists in detecting, logic that performs labeling, logic that validates the labels generated. Our technical view on distinctibility, traceability, linkability drove us to build this pre-process, post-process approach. We'll cover more details on the agent later. As we better understood how to make our agent compatible with our enterprise data, we quickly realized the organic nature and scale of the data we were dealing with. For some of the researchers who are more accustomed to clean, ideal data, understanding these characteristics was very helpful in accumulating experience around the gaps between the real world versus the ideal world. For us to scale, we needed an approach that relied on guided detection and classification of data. To pragmatically address scalability, we elected to go with the approach of detecting for the common and majority case, with the assumption that personal information would be concentrated in segments that were a majority. We reduced the inspection scope using hints in metadata and schema. We chose specific segments that covered a common case viewed as a representative partition. Once we scoped it down to specific partitions in a table, we queried for common case terms and semantics to reduce the categorical scope of what to label. For each column, we selected common terms and semantics and used these subsets to label personal information within a column. Another aspect of what we needed to look into was, in terms of pre-processing, is scoping variability of data structures from a data source. We found, depending on the operational model and processing workflow, data structures vary from data source to source. The level of repetition needed to evaluate each individual data element and the way data types are nested varied a lot. So we started using simple ways to transform the data into trivial structures with the goal that as we collapse data into trivial structures, we'll learn how to build them up one by one into a form that is most effective for us in the future. Unfortunately, we haven't quite been able to build out those templates yet. Those data types and relationships, we're still experimenting them. But what we're finding is this collapsed structure is helping build those insights that we'd like to experiment and research. Once we collapse data coming from a data source into a trivial structure, we apply the techniques we talked about on scalability to the simplified structure. Now that we've explained how we massage our data, it's ready to be labeled. The massage data runs through the labeling logic. We use a combination of dictionaries and ML to label data. Any method we know produces inaccuracies and uncertainties, recalls and precisions. So we've managed to build technical constructs that are tightly coupled to our organic workflow to improve our knowledge base in labeling data. We first talk about dictionary-based approaches we've used for labeling. Dictionaries are a good set of activities to detect and classify well-known and well-structured personal information. Dictionaries validate all aspects in personal information: traceability, linkability, and distinctability. We constantly monitor metrics from our agent while simultaneously performing offline simulations to look for areas of improvement. Both activities trigger alerts and subsequent activities on anomalies and unexpected behaviors. On alerts, we investigate the cause and revise our labeling knowledge base. We push our updates into production and close the alert. Our knowledge base comes from known practices in data science. Unfortunately, there is still a bit of art tied to this activity. While we showed here our workflow based on dictionaries, these workflows equally apply on how we label using ML. Next, we'll talk about how we use ML to label data. For certain types of data formats, semantic variability, the relation to language, logic, and culture, it seemed inevitable. As a global company, we face challenges tied to difference in semantics for each region in the world. We found from our experience, ML best copes with this type of variability when carefully understood and applied. For example, language-dependent aspects of a name exist as well as the origin of each unit within a name. Culture-specific behaviors in the format of a name and how it's contextually expressed varies quite a bit. Instead of addressing this issue in a country-specific manner, we're vigorously trying to build generic approaches that abstract out the semantics. And making sure we find ways to train our models to understand these semantics has become an important priority for us. To date, we found linkability, traceability-friendly models are developed to infer indicators and context for language, as well as culture-bound forms of personal information. Once we produce a label or multiple labels for data, our agent goes through a post-processing phase to filter out and validate misleading labels. We apply application-specific filters that reflect context and statistics. We check validity using computation and comparisons for knowledge base we've compiled on that data type and format. With respect to our technical view of personal information, filters clean out linkability and traceability. Validations confirm distinctability and traceability attributes. We show a post-processing example here where there are 4 labels produced for a column. The contextual filter eliminates the birth date, as we could not find metadata and schema indicating this date is a birth date. We further eliminate name looking at the statistical properties we found for elements labeled as name. Computing and comparing email and address properties revealed email to be the most probable label. So now that we've given you an overview of our technical approach, we've described that in the prior slides, we think it makes sense to tie our approach together and show an end-to-end example. After we go through the example, we'll link it back with what it means for data handling and data disposal. Our example starts by inputting a data stream that is really a table composed of multiple segments and composite data types that are nested and repetitive. A detection logic in the agent addresses the scalability challenges and the structural variability using our described approach, and produces a single partition collapsed structure with multiple values. Our example shows columns with the name foo, bar, baz that contains values that need to be labeled and evaluated for personal information. The data stream is scoped down to a single partition and a common set of terms and semantics. Once we've scoped down the data stream, our label logic assigns multiple labels to each column. Our example shows for the foo column, we have a label tuple for name, address, and phone. For the bar column, we have a label tuple for email and name. And finally, for the baz column, we have a label tuple for credit card and region. While this example may appear to be hypothetical, if you look closely, the labels themselves are what we actually handle and utilize in services such as Samsung Account and Samsung Pay. The label tuples then go through the evaluation logic, the many filters and validity checkers we have to produce a ratified label. In some instances, it will be labels. Our example produces the name for the foo column, email for the bar column, and region for the baz column. Now that we've obtained a well-labeled table, the set of labels and data tied to that is ready to go through a data lineage. So with labeled data, we are now able to use this label on other key elements in data protection, in particular data handling and data disposal. For encryption, the data label drives management of the key and forms of encryption of data at rest in particular. The label data also assists in the act of de-identification and evaluating the risk of re-identification. Both of these aspects, de-identification and re-identification, are very important in handling and controlling the footprints of anonymized and pseudonymized data. Labels also play a key role in computing of the data. Privacy-sensitive compute techniques such as confidential computing can help in keeping data safe. And finally, while it may be counterintuitive or less obvious, label data can help to generate synthetic data. While this area requires more research, we found advancements in labeling personal information helped us make advances in what we know and how we should view synthetic data. With respect to data disposal, labels that include categorization of personal information drive the retention time and disposal of data. We understand the final stage in a data lineage is disposal of data. We know this activity must also be responsible and transparent. This table shows an example of how labels set the stage for data disposal policies and workflows. Now that we've provided a description of our technical approach and into an example, we'll describe this technology in action. When we say in action, how it's deployed and used within our enterprise environment. So we'd like to switch gears a bit and provide some background on how we view data as a whole. Samsung provides many devices and services that are getting smarter to provide better service and for your experience. For us, data is a foundation for this intelligence. And most companies utilize big data platforms to process data that comes in different forms and sizes. A big data platform is usually composed of 4 functions. Data discovery, this function builds a data map and helps us find out the data we have. Data access, this function defines who can process data. Data analysis, this function enables insights by processing data. And data utilization, this function improves the service or intelligence of devices by processing data. We need to both innovate while responsibly conserving privacy. This is the reason why we revise the big data platform to be a data privacy central. The 4 revised functions for privacy central are, or data privacy central are, privacy discovery in place of data discovery, encrypted access instead of data access, anonymized analysis in place of data analysis, and finally, secure utilization. We'll briefly cover these 4 functions in the next slides. With respect to privacy discovery, data is complex and spread over multiple systems. This is where our technology for detecting and classifying personal information, described in this talk, was deployed as a key component for the PII detection system. This collects schemas and samples data autonomously. Privacy detection is done as early as possible and audited throughout the entire process. We construct a personally identifiable information map for the tag data which is stored in the data warehouse along with the ingested data. Tagged information is fed back to the data source system for their own tagging and review. Once we identify personal information, the next step is protection. To ensure the safety of this data, data encryption is applied over all personal information. We use column-level encryption, which is applied as early as possible. We store personal information in an encrypted form in the data warehouse. We take additional measures to restrict access to this encrypted data to a limited party. Encryption persists throughout processing the data. For example, when joining two tables, the encrypted columns remain encrypted. In terms of analysis, we apply anonymization of statistics wherever possible. We use analytic tools to measure the potential of re-identification of statistical data. We adopt k-anonymity as one analytic tool to assist in this process. When utilizing data, we need to ensure personal information is kept protected as much as possible. We provide end-to-end protection that keeps data encrypted as long as possible within its lineage. So to wrap up, without privacy technology, we truly believe it's challenging to realize data intelligence. Our ultimate goal is to deliver an excellent device experience to customers. We've evolved our big data platform to become our data privacy central. The automated personally identifiable information detection technology allows us to enable responsible access and analysis of data. Our privacy philosophy enables us to deliver smarter devices to customers, data intelligence to businesses. We don't think this is the end of our journey. Please follow us on future updates towards our journey for responsibly handling data. Thank you. So the original intent was we take questions offline and we can talk obviously in the corridor, but since I have a couple minutes, I'm more than happy to take questions here, see if I can repeat them, and then we can carry it from there.
Thank you. Excellent, cogent, clear presentation. This is what we expect of the top people at Samsung. I'd like to know what you see as the differentiator on your ability to encrypt and secure data at the column level. I assume if it's column level, that assumes it's in an actual relational database, and we think that's actually the problem. What's your view of hypergraph databases like Gun.echo and Secure Render Community and other approaches that we think can do it either in JavaScript and browser, maybe in a quantum secure way, maybe tying into the Samsung quantum encrypted quantum random number generator encrypted hardware,
okay,
and other solutions that could work in the way the rest of the world actually works.
Okay, so if I understood the question, what is our approach for encryption and the role of cryptography? Securing data at the column level, okay. So I think the answer we could give you at this point is we're still experimenting. I think obviously one of the concerns that we have when we try to adopt encryption and cryptography is how much overhead does it provide? How much throughput? What's the asset that we're trying to protect? And it may sound as though it may sound as though it's not a one-size-fits-all answer, but what we found is it depends, unfortunately, today. It really boils down to our budget that we have, so we're trying to use as standard approaches as much as possible. We are, however, researching ways of looking at more exotic cryptographic protocols, such as what you've just mentioned for homomorphic encryption, and such as what some of the other elements that could exist even for format preserving encryption. Those are research-wise more things that we should look into through the broader horizon. Yes, we are in the forefront when it comes to cybersecurity and becoming attacked. So that also means that we should be more responsible in selecting the right cryptographic algorithms and so forth and putting that together.
You can't, like that's why DARPA and NIST are doing
Yes.
a contest to bake off. And one of them got hacked, but when chose for an open source version, they got hacked by
Yes.
I think the big thing you've done, which no one else has done, is you built hardware that actually has encryption in it. It has quantum encrypted hardware in it that others can build on. No one else is doing that unless you're in.
Well, there are others, to be more precise. However, I'm starting to look at time, so I'm more than happy to take this offline. Should we end the talk or? Okay. Unfortunately, I think my time is up. So any other questions, we can probably talk offline. Thank you again.